Hello everyone, thank you for coming. So today we are gonna explore general and new concurrency pitfalls and some recipes how to avoid them. My name is Farrukh and I'm a lead software engineer at EPAM. So I'm at EPAM working since 2022, but I started my professional IT in 2007, programming in Java since 2010. So this is so today's agenda, we are gonna briefly, very quickly, give some introduction in what the Java concurrency is. Then we move to actual scope of the session. It's considering exploring race issues. So we are going to explore data race and race conditions. Then we move to visibility and memory consistency issue, one of those vital, fundamental hazards which you may face when you develop actual concurrency code. So we are going to explore the liveness issue, deadlock, live log, and starvation. Then we quickly take a look to thread termination, explore some approaches, how to correctly terminate threads in order to avoid some issues or pitfalls regarding termination. Then we will explore all virtual threads and hazards, or actually pinning pitfalls related when using virtual threads. Okay, let's start. So as all you know that Java pretty mature language. Threading was introduced from version 1.1 and 1.2. From here, fundamental threading, runnable tasks, synchronized, and so forth. So I would like you focus on your attention for JMM. It stands for Java Memory Model, which is vital in order to discover those pitfalls we are going to explore. As you know, Java evolved and improved its toolbox for concurrency, introducing stuff like threading pool, executor servers, and so forth. In Java 1.8 was introduced major enhancement and new features like completable feature, parallel streams, and classes atomic. And in Java 21, which is actually long-term support, LTS, most project already migrated to this version. We are going to discover virtual threads and related pitfalls when using virtual threads. Okay. Okay, why we need actually reasons? These are reasons why we need actually concurrency. Of course, it's about performance. It's about responsiveness. It's about effectively utilize CPU machines. For example, nowadays we have multi-core CPUs. So in order to prevent some idle, actually server-side code should be much concurrent as possible. Of course, it's about scalability. But even you don't write everyday performance or concurrent code, you will face concurrency in JDK, in certain frameworks like Spring and other like Quarkus and libraries. So knowing those fundamental pitfalls and knowing those fundamental approaches and scenarios how to avoid concurrency hazards is vital. Okay, what we have threads, like fundamental entity in Java concurrency. At the same time, we have challenges when programming with threads. So, as all you know, thread is a lightweight process. It's a unit of execution for concurrent code. At the same time, we have challenges, like, for example, when multiple threads communicate or exchange via shared variable, things went wrong. Concurrent manage access to shared variable should be managed. So uncontrolled access to share variable can cause consistent or corrupted data. We will explore those scenarios of corruption. What we have, Java provides us fundamental tools like the thread class, synchronized constructs, volatile keyword, final field, and the Java memory model before rules. These are fundamentals in order to write truly correct concurrent code. But at the same time, we in our toolbox as a Java developer have some frameworks provided from built-in concurrent frameworks. So these are like executor services, fork join frameworks, atomic variables, primitives for synchronization, asynchronous execution, and of course, Java 21 was introduced virtual threads, which actually can be created without significant code requirement. In most cases, this doesn't require any refactoring, so it's eventually we will exploit just thread class. But under the hood, that works differently. Okay. Also, we have concurrent collections in order to process multiple elements concurrently in our concurrent code. So Java 21, virtual threads, structured concurrency. Actually, structured concurrency is preview available. It's not officially stable, but virtual threads already declared as stable. So in the production, you can use without any fear. We have for those pitfalls causes, some fundamental causes or main causes and consequences. So one like data corruption, undesired incorrect outcome, performance, all those come from such causes like interleaving of operations, absence of sufficient synchronization or coordination, ordering of operations, timing or scheduling of operation by JVM, by operating system, and caching. For example, JVM may optimize and cache those shared variables. CPU at the operating system can cache in its register and caches L1, L2, and everyone knows, right? Okay. What is actually race? Race actually is competition between threads on a shared memory, right? So most concurrency bugs are race bugs. So race can be categorized in data and race condition. We will explore, but most developers, like, not sure how do you think okay, there is like maybe it's just data race and its condition. It may be some subset of another, or it's the same equal stuff. But we will discover these are completely different things. Okay, data race definition given from the Java language specification. So when a program contains two conflicting axes, and if at least one of the axes is write operation, and if they are not synchronized properly. So this is data race definition given from Java specification. Here by synchronized, this is not the synchronized synchronization. It's not synchronized construct. It's in general in one term. So it can be synchronized, volatile, log, and so forth. This is just about coordination. We can, there are two actually race, even data race are harmful. It causes like bugs, but there are also some benign or harmless bugs, which, for example, expert in concurrent coding in order to use less synchronization, but at the same time, for the sake of performance, they code in such a way it has like some benign race, just for not using extra synchronization overhead, locking, and so forth. We will explore. I wouldn't recommend like try to write for the sake of performance benign race code, but just knowing that can be achieved in order to give much performance when you like becomes like significant like expert in such area. But even I like with such having such skills experience don't like. I try to cover all those synchronized code, trying avoid them, even those are benign. Now, race conditions. Actually, this is a logical error, not technical like data race. For example, in case of data race, when we have multiple threads accessing at least one of the access is right, bombarding memory, it's not. Race condition is illogical, non-deterministic. It will impact logic of your application. For example, negative balance of when you develop some money transfer code. So this is like a logical issue which actually should be avoided. It should be tested and properly handled. Okay, there are two categories of race conditions. So those can map in general for those for such two patterns. For example, you have read modify race condition. For example, a post increment actually does read, modify, and write. Meantime, for example, if some threads does some read, some thread already raise it to the modify. That's why you will have inconsistent data. So this is right. Second category, second types of race condition can be seen like check then act. For example, if you run multiple threads, one of trying to check if an instance is null, whether or not null, second or third thread may already populate this. So this interleaving causes a race issue. That's why we need proper synchronization or coordination. Yeah, let's consider one example. For example, this is a hypothetical money transfer code. For example, this is simplified. For example, don't use this in your production code because account from and account to never should be int. It actually should be some proper object class which contains proper big numbers, not like single like int. So nevertheless, this is just for the sake of demonstration and user race state. This code has both data race and race conditions. And race condition type of is modify right. Because we have account 2 plus equal amount, but at the same time, it can be considered race when we check if balance less than amount, we consider it as a check then act data race. But most importantly, it's race condition and has both data races. Okay, yeah, obvious approach is to wrap this code into synchronize it. So this will be from data race and from race condition because we are using mutual exclusion lock, mutex. But it has drawbacks, like, for example, if one thread hold the lock, the mutex locks, other threads will be blocked and will try to do an unuseful job. Like this is just blocking. So it's high cost of suspension overhead, no ability of thread termination. In this code, we little bit race free try lock MT, we little bit improved this. Instead of synchronize it, we use reentrant lock in order to avoid that suspension overhead. This still has suspension overhead by its law, because the threads which couldn't achieve the lock won't be blocked. It will be free. CPU can use that thread somewhere, some logic elsewhere. So all those logics flow drops to the else section. So this also have other advantage like ability of termination and fairness. This is more improvement. We are using atomic variables in order to give much performance, like avoid any locking suspension. We are take advantage from the CPU compare and swap approach, which is in CPU level. This is optimistic concurrency. So for the scope of this presentation, I didn't benchmark. Okay. This code should run faster than trial lock and faster than synchronized block. Race condition, but free from data races. This is just, for example, in order to show we have a data race here, but we we have a race condition because of atomicity issue, because volatile, as you know, provides visibility but not atomicity. That's why we have race condition but free from data race. Why free from data race? Because JVM says if you declare your field and that field is shared, there is happened before relationship that thread which reads, threads which writes to that volatile field happened before that those other threads which read from this volatile. That's why there is no data race, but because of atomicity, we have a race condition. Now, this shows that category of race which is benign or harmless. For example, I just introduced it for synchronized transfer is processed Boolean, which is not included in the synchronizer. Also, it's not it is not a volatile, so it's racy field or racy memory. So threads may write to it. So it's, but this should be used like for some approximate statistic, because this, for example, even like threads write, multiple threads write true. We don't care from logical perspective. Is this transfer or transaction is processed? No. That's why it's declared benign. But this is a simplest example of how benign race may look. But we will take a look how GDK has such race, data races, benign races, which is fine. Yes, this is like summary table of those class we explored. So for example, thread interrupted logic is erased. It's just Boolean without any synchronization, without volatile, but it can be used without any fear. Summary, always synchronize code to avoid thread races, use advanced log. This is scenario. If you can write atomic algorithms, use atomic primitives, use volatile field when it's applicable. For example, it's applicable for checking something, because volatile are less expensive from overhead perspective than synchronizers. That's why volatile should be used when it's applicable. Also, we will explore final semantic for safe publication and safe initialization. Okay, I would like to show one code regarding these. Okay, I have prepared a few. Okay, Yeah, this is a naive approach how you may test a concurrent code. This is naive, and this is not like actually expert does. For example, expert like use some framework prepared for, this is like experimental framework. It's used by JDK developer in order to examine those race or other concurrency hazards in OpenJDK. And author of one of the known author of this tool is Alexey Shpilov, concurrent guy in Java world. Okay, so this is the same things, but with more professional tool used. So this here, actor 1, actor 2, actually 2 threads which increment the count. So outcome for this, so this is a shared, this is volatile. So here we are demonstrating volatile. Because of volatile provides visibility, and because it's not atomic, we will expect, for example, such things. For example, if 2 threads increment 1 count, it actually should be easy 1 and 2, for example, or 2, 1, but it shouldn't be 1 and 1. But in this code, this actually checks that this interesting is happening. But moving to our actual code, for example, the race MT test, this actually tests a class we explored in presentation for this transfer. When you run this test, it will give you such things. So all these other cases produces race is samples of the try to figure out whether or not this code is racy. Obviously, it's racy. So because it's not used any synchronization. Race volatile approach for the same things. It gives little bit different, but because of atomicity, it's also racy. All these results I just prepared. You can clone this from my GitHub repository. It's accessible. You can run on your machine and make sure you will give some approximate results, because, for example, my machine may differ from your machine. So if we, try log. So this is, as we can see here, try log free from race, and we get, for example, if we transfer 100 and 200 with 2 different threads, outcome should be whether 300 and the other, for example, 900 and 100 also outcomes also valid, because, for example, it says that we one actor 1 or threads 1 made correct transfer. Meantime, actor 2 was asked to do something, because we are not because we are not blocking, we are trying other threads results. Other threads try drop here. That's why we have such outcomes. So let's move. So if you want, you can like actually clone this offline. You will check because of format of this session that it doesn't allow me like. But actually, let me try check and then act quickly. This is how you can examine, check, then act race issue. Actually, JC Stress does its best in order to break our code to try to discover races. So whatever you see boring, we are expecting. We are expecting 1 here, for example. This code says if this is not like null, so we are getting 1, and if it's null, so we are getting like -1, which is like a mock. We just mocking in order to figure out. So yeah, so it will use multiple JVMs in order to break and dust trace in the JVM with different parameters. So this is happening. As you can see, it runs like multiple. Okay. Meanwhile, let's move forward. Let's discover visibility and memory consistency issues. So it's about partial constructed, stale object. So it's about reordering. Reordering may happen by compiler, by JVM, by operating system, by CPU. So they are free to do reordering because of performance. These are factors which can impact to the visibility issue, as we already discussed. Yeah, we already told about this. This happens before. Guarantee given by Java memory model. Take a look, and this is a fundamental guarantee which Java provides us as a tool. These advices use advanced log instead of synchronize it or take advantage from atomic variables. Now, I would like to quickly, how many time? Okay, 5 minutes, I guess we start. Okay. Safe publication, safe initialization. Because constructor is kind of method for threads, whenever you initialize a constructor, that should be thread safe. That's why there is like final field semantics, which guarantee self-initialization during object construction. It's about use mutable object whenever it's possible. Safe publication is not guarantee, it's practice. You should master it in order to safely publish reference to object when that reference is shared between multiple threads. So this is also fundamental concept in concurrency. So you should take care here. Yeah, this is like summarization of what we said. So yeah, we already considered it. So these concepts are fundamental: visibility, ordering, atomicity, safe publication, safe initialization. In order to avoid, if you master this stuff, you avoid those concurrency pitfalls which we discovered. Yeah, liveness problems. This is practical issues. For example, if you write incorrect code, it may lead to deadlock. If you write incorrect concurrent code, it may lead to live locks and starvation. So some necessary conditions which cause these liveness problems. It's about exclusive access to multiple resources. Threads wait for each other to release the resources. There are circular wait or infinite blocks. These are practices. Minimize lock scope, minimize holding time. Don't do blocking I/O complex logic while holding a lock. Abort or restart approaches like deadlocks. Okay. One of the key I like in database, for example, if you write transactional code in database, there is like find victim and kill that transaction in the RMDBS relational database. But Java, because we are opening our code, Java doesn't resolve deadlocks. It doesn't pick some deadlocked threads and kill that. That's why I like DB transaction is much better than like JVM. But at the same time, it's about ownership of the code. So we don't own database transaction execution, but we own JVM execution. Yeah, it's tooling, analyze deadlock with thread dumps. In my repository, I have a few showcases how deadlocks may occur. You will get familiar yourself when you pull that code. Yeah. Okay, thread termination. This is a popular subject in Stack Overflow. That's why once you started your thread, you should also think how to properly terminate, because it's about racing car, right? So you run, you should also during race you should be able to correctly terminate in order to avoid such issues like resource allocation, corruption of data, and so forth. Like, yeah, always clean up resources, and these are like recipes how to avoid termination issues. Let's discover some interesting part of this session. It's about virtual threads. Virtual threads introduced, I believe, in JDK 19, but now it is production ready. But it is not replacement for existing tools like thread pools, fork-join frameworks, but it has its own usage. Whenever you want to develop thread per request style, now it is time to use virtual threads. It's still java.lang.threads from interface perspective, but under the hood, it's different. Yeah, this is an abstraction how virtual threads is implemented. For example, there is like many to one, so you may have created multiple virtual threads carried by platform threads by one, for example. That's why it's cheap to create, and it's scheduled in JVM, but not in operating system when actually platform threads is scheduled. So the gain here is scheduling. The algorithm of scheduler of virtual threads allows us to create many virtual threads when the requirements requires from us. So virtual threads is carried by platform threads, normal threads, what we have in classic term. It's scheduled in like different carrier, so it's independent of its current carrier. Carrier threads is just platform threads. Yes, there is an issue like pinning pitfall. It's actually not the logic. It doesn't lead actually to logical issue like race condition, but it impacts to the performance. So pinning means when multiple virtual threads carried by one, for example, platform thread, there is a chance that concurrent written code may pin. So because there is like mount-unmount logic implemented in the VT scheduler here, that's why it's called pinned. We are going to explore this guy. Scenarios when it may happen. When using synchronized block, pinning due to native calls and pinning caused by blocking methods. Like, these are recipes how to avoid. Yeah, okay. I would like quickly show the pinning issue, just not to be liar, okay? Okay, this code actually demonstrates virtual threads and the pinning issue. In order to debug pinning, we should run like our Java process with -dgdk trace pinning pitfalls. So actually, it's in here. So when we run this guy, this is last. Okay. Hopefully, we will observe that pinning. Oh, okay. It's quickly discovered. Reason monitor. Monitor is synchronized, mutual exclusion. And this is like print tracing. So under the hood, it's fork-join pool. Scheduler wraps our virtual threads in the, so this is like, but finally counter prints correct result. So even, for example, we tried increment from 0 to 100 for 2 threads. So we eventually got correct result, but we got some performance. No pinning approach, the same code, the same logic, but because of we reduced blocking, this code doesn't, in this code, virtual threads don't pin. Yeah. So this is like simple counter. We are using try lock. Yeah. No pinning. And we run with tracing. Yeah. JDK trace pinning threads. Yeah, these resources can be used to get deep dive into the issues we discovered this Java language. And actually, this workshop is submitted in this. You can pull and experiment on your own. That's all. Yeah.
Good morning, Farrukhjon. I have a couple of questions regarding, not for this session, but overall regarding the Java web development. So first of my questions will be, do you use the Spring the most of the times for building the applications in EPAM nowadays, or do you prefer another frameworks like Quarkus or Mycanow?
Okay, even this is out of scope the session. It depends. It depends. For example, recently we actually Spring is mostly used, but recently we starting to develop some small microservices in Quarkus framework. Because of requirement. If like clients won't use small stuff, you can use small tools, but make sure the tool or framework is mature enough. That's true.
And the second question will be,
Please.
just hold it. Oh, okay. So, and another question will be, did you start to use the virtual threads a lot nowadays? Because if I'm not mistaken, uh, the most developed tool for the developing web applications, the not blocking web application is Spring Web Flux nowadays. And did you start replacing Web Flux with the virtual threads, or is the Web Flux dominating nowadays still?
Yeah, there is like this is like actually good questions which address it with a latest item. If you are using asynchronous or reactive stuff, don't use virtual threads. Use that library.
Yeah.
Because virtual threads address other stuff. It's request per thread.
Sure.
So that's why this doesn't replace completable stages, completable features, or Reactor project or RX Java. This addresses different stuff. Yeah.
No, if you start using the virtual threads, if I'm not mistaken, the virtual threads and the reactive programming seems to achieve the same goal, if I'm not mistaken. It's, the parallel... можно сказать на русском?
Да.
Я немного затрудняюсь. Если я не ошибаюсь, то вот виртуальные потоки и вот реактивное программирование стремится достичь одной цели – параллельной обработки запросов, правильно? И мой вопрос заключался в том, что я бы хотел узнать, вы уже заменяете вот именно реактивное программирование и точнее Spring Web Flux виртуальными потоками, или все же виртуальные потоки не готовы для production ready кода?
Virtual threads addresses different. As I said, there is a pattern, thread per request time.
Yes.
Reactive frameworks and asynchronous, there is a reactive manifesto. There are 4, I believe, like stuffs. For example, reactive streams. If you are developing reactive streams, there is nothing to do with thread per request style. For example, if your application thread per request style, go ahead and use virtual threads because there is no other fundamental. Maybe you can like work around, but we have already prepared tool. But if you have asynchronous application, asynchronous stream, Internet of Things, for example, your iron gonna send huge number of messages to the cloud, go ahead, use reactive tools. Don't use like virtual threads. This is a recommendation also from Java specification.
Okay, thank you very much. I have no questions left.
Any other questions? Actually, we are out of time, actually. Yeah, please, in the scope of the session, if you have, or something is not clear, you are welcome.
Then thank you. And we will our next speaker.
Спасибо. Sorry.
Слышно, да? Слышно, да? Ага. Супер. All right. So we're gonna start in a moment. Yeah, sorry guys for being late. There was a terrible traffic jam on the road. So yeah, let me introduce myself. So my name is Javokhir, and as my name suggests, I'm a Java developer here at EPAM and working for more than 3 years at EPAM company. And in overall, in Java, I have more than 5 years of experience, production experience. And today we're going to talk about a Java virtual meal, in fact, yeah, an example of the virtual kitchen. So we're going to slightly dive into the JVM architecture, and we'll talk about the main components of it. And also, besides my work experience at the EPAM, also one of the drivers at the Java community Uzbekistan. So yeah, if you guys like that kind of contact, yeah, please like and subscribe. And if you have any suggestions or feedbacks, please reach out to us. And then we will try to make such kind of contents even more and even better in different concepts as well. So okay, without further ado, let's get started. So first of all, we have the agenda here. So we're going to start by exploring what is the JVM itself, and then we're going to talk about briefly about the JVM architecture overview, and then we're going to actually use the kitchen, real kitchen as an example of the reference of the JVM architecture. And then we're going to talk about its main components, which are the class loader, runtime data area, and then execution engines, garbage collectors, and etc. And we're going to talk briefly about some of the pitfalls we might have when we are working with a JVM-related machines, and how can we solve the problems involving our JVM. Okay, so here we have the JVM architecture overview. So mainly, this is the, I would say, holy grail of the Java developers. And by the way, I believe all of you guys are the Java developers, right? Or do we have anyone like from the JavaScript or like non-JVM, the languages which don't use the non-JVM architecture? Or only you, or a couple of guys? Okay, you may actually go out from here. That's a joke, okay? So don't take it seriously, okay? Yeah, you're welcome, guys. Yeah, we actually love it, especially for the JavaScript developers. If somebody, or like if the people who coming from any scripting languages to use the JVM language, we are happy because we actually want to kind of advertise our language as well to have a better developer experience. Okay, moving back to our topic. JVM, actually the machine which is inside of a Java runtime environment, yeah, GRA as a short. And GRA contains besides JVM, we have library files, yeah, which will be necessary for the Java to upload during its runtime. And then on the bigger picture, we have a JDK, yeah, Java Development Kit, which includes the JVM, GRA, in fact, the GRA itself, and then some of the dev tools like Java C, Java compiler, Java dog, and etc. All related to the Java command line utility tools like prior to, for example, Java 8, we used to have a Visual VM, which was used for the monitoring. We will touch about that a bit later. And also we have the Java console, right? And other utilities which we can use for investigating memory JVM related issues. So in fact, how the process of the code execution happens in our JVM when we write the code in Java. So usually it has a Java extension code, and when we load it, when we run our application, what happens? In fact, at first we need to compile our Java code into the class file, which is a bytecode, like bytecode instruction of the Java itself. And then, as you might see, Java source code using the Java C will be compiled into the .class file extension. And then that .class file extension will be loaded into the JVM. So this is, in fact, we can see that this is can be example of the JVM, but mostly here we have the example of the compilation process, just-in-time compilation. So we should not actually confuse it with a compilator and the compilation. GIT compilation is a part of the JVM, not the compiler. Okay, so after the class has been created, it will be loaded into the class loader, and then class loader, like in our kitchen example, we can actually say that receipt manager, yeah? So the bytecode instructions can be considered as like receipts, yeah? For example, if you come, as we actually talked about it, the JVM is like a kitchen itself. It has a chefs inside, it has a fridge and all the necessary products to make some beautiful meal. And the people who are coming, like we might say, like for example, this is a kind of process happening inside of our application, right? So our restaurant application is built on top of the JVM. So restaurant can be an example of any application. And the kitchen inside of that restaurant can be considered as a JVM because JVM is a backbone of our running application in Java, right? Okay, so the class loader is a receipt manager. So the code execution is instructions, receipts, yeah, to prepare the meal. For example, what we might have for preparing the plov, for example, yeah, we might have some rice, some meat, and some like carrots, yeah, to prepare the meal. So the receipt manager actually knows it and the receipt manages what kind of receipt, like ingredients, should be involved in the process of cooking the meal, yeah. For example, if you wanted to prepare the plov, you don't need an ingredient for the kebabs, right? So that's why all the necessary stuff will be loaded into the class loader. Otherwise, we might have out-of-memory errors, which is really bad, yeah, if we load everything. And then after the class loader, we have every ingredients that we have to prepare some beautiful meal. And then we will have a method area. Yeah? Right now, this is a mostly like just-in-time compilation. The method area where the objects were being created, where the meal preparation is happening. And then we have interpreters, executors, yeah? Like we can say that they are the chefs. Like interpreter, for example, we'll talk briefly about it, yeah, in the next slides as well, are like intern chefs. Yes, they actually read line by line about recipes to prepare the meal. And GIT compilers are like more experienced chefs. Yeah, they know the ingredient, they know the recipe by heart, so that they don't have to refer to the instruction like over time, because once they look at it, so they remember, and every time the new execution, for example, for the plov will come, they actually remember that one, and then they actually can reproduce that execution by their memory, yeah? So in fact, the GIT compiler does the same. So it actually caches the code inside in order to have more optimized code. For example, we might have a for loop, yeah? So in order not, inside of a for loop, we might have some assignment for the local variable, right? So interpreter would be actually, every time it has to actually read it line by line and do the assignments, but for the compiler, it already runs it, knows it, what was the previous value of it, so it actually gets the value from the cache as well. Okay, we will talk about, yeah, that was the example that I was referring to, the kitchen layout, right? So this is our main GVM model. So in fact, the class loader, as I mentioned before, this is a receipt manager, yeah? The person who is responsible for getting all the food, yeah, all the ingredients. So it's like a kind of the person who runs the storage, yeah, who actually responsible for like giving the people some food, the chefs some food, yeah, some meals, some ingredients to prepare the meal. And then next, runtime data area. This is the shared memory area, yeah. In other words, the shared memory area, we might refer to the heap. In fact, stack is not a shared method area, and the heap is a shared. So as you might see that, for example, as an example of the shared zone, we can refer to the fridge, because fridge is being used by the multiple chefs, yeah. For example, if you wanted to, if the chefs get requests to prepare the plov, yeah, one chef come to the fridge, to the heap, and then take what they want, yeah, or like store what they want, yeah, some kind of product, yeah, component of their meal. And besides of the fridge, we may refer to the common area where the meals are being prepared, like a pot or like stove, because they are being used by the multiple processes, by the multiple chefs who are cooking the meal. Okay, so this is the layout of our GVM. So in fact, the class loader contains three phases, yeah, loading, linking, and initialization, yeah. In the loading process, we actually load what we need, as we talked about it before, and linking, we actually link related components, and initialization, we actually initialize the static like variables, yeah, in our application. So this is what the dynamic linking resolution happens, yeah, like some kind of initialization related to the static blockers will happen inside of initialization. So in fact, in this diagram, we have like small pitfall, or like a mistake, or like not a mistake, but something like a bit outdated component. So yeah, who can actually highlight that one? Yeah, just like, yeah, like in these components, yeah. Who can actually highlight? So if the person can actually, yeah, find that one, he will get a 500 points to their karma, like to their knowledge base, yeah. Because we don't have a presence yet. Sorry for that. But for the next time, we'll prepare some really good presents for the really good questions. So anybody can? Okay, I'm gonna give you some hints, guys. No. It's for example, yeah, I might give you some hint. This is the architecture of the Java 8 memory model, GVM for the Java 8 version. But after the Java 8, in Java 11, so in the other LTS versions of the Java, like 17, 21, we might have we have the slight different representation of one of the components here. Any questions? Yeah, please go ahead. Not that much, because we still have the method area, but that was a bit close. Okay, and any you may actually. Okay, I'm going to give you another hint. You may actually pay attention to the class loader. Yeah, class loader. Application loads our JVM. It's not and it goes to extension. After that, then
I mean,
well, in fact, the hierarchy is like, depends on how you actually look at it, yeah? For example, in terms of the delegation model, you're right. For example, at first, application class loader refers to its parent because they are actually like created in that way, yeah? They actually, because they are polite, they ask the permission from their parents, yeah, ancestors, before moving forward. But you actually missed one point. Still, these are the components of the Java 8, because delegation and like delegation model is like that. Because if they cannot find, they go in that direction, in a top-down direction. But in the delegation, it's like bottom-up. Okay. Any more? Yeah, please don't actually let me lose my hope. Any? No? Okay, I'm gonna tell it. No. This is only, well, garbage collection. Yeah, we have the different versions of the types of the garbage collection. You're like slightly right, but in fact, yeah, we don't have the garbage collection image here. In fact, we have the extension class loader in the Java 8. And right now, like in Java 21, Java 17, Java 11, we have the platform class loader. So the extension class loader was replaced with a different class loader. And also, yeah, right now in the Java 12, 21, and other versions up to the Java 8, we have the application, platform, and the bootstrap class loader. So here, you might see, yeah? And user-defined also like can be called as a kind of custom, yeah? We could actually create that class loader in the Java 8 as well, but also, yeah, it's possible in other versions as well. So yeah, types here, the bootstrap, platform, application after the Java 11. That's the process of the loading, yeah? So it's like you actually define, yeah? Like for example, application class loader loads the data from the class path, yeah? It can be dependencies of the application, yeah? If our application is a Spring. And then the platform class loader is a Java C platform, yeah, APIs, which is actually Java 11's library. Prior to it, that was the extension, and it was like used to load from the rt.jar jar file to, yeah, like, and then like bootstrap class loader is from the gmods, yeah. This is after the Java 11, because in a Java 11, we have the one big change, architectural change in JVM. Who can actually tell that? What was introduced in the Java 11? Modular structure. Yeah, modular structure of the application, because we are going to we can actually like split our application into the modules. So that's why we actually loaded from the JMods. Yeah, prior to the Java 11, it was like non-modular architecture, but mainly in a production, we rarely use the modular application because, yeah, we refer, but still there are some talks for going back to the like modularity, yeah? So it's like modular application can be kind of used as a modularity, because like we are going back from the microservice approach to the more like a monolithical approach, yeah? Like as we see, for example, in example of some big tech companies moving back from the, for example, Netflix and other guys, yeah, Amazon, switching some of their architecture from the microservice to the monolith because of the money, yeah, because microservice takes more money if they cannot be justified with a scale. If the monolith can actually handle the load, why not use the monolith itself? Because it's actually much cheaper and more easier to debug the application. Okay. So the next slide, runtime data area, yeah, the kitchen's working surface, yeah, as we talked before. So the shared memory is like method area, heap, and inside of a heap, as we talked before, all the objects were created, yeah. And then, and another part of the Java memory is a stack, and the stack is a thread-based, yeah. So each thread, they have their own stack, yeah. And so this is not the shared memory, yeah. stack area. Inside of a thread, we have the PC registers, yeah, to know which the stack is being executed, which method we're being executed, in fact. And then native method area. So native area, which is like through the JNI interface, Java native interface. Actually, for example, in our kitchen layout, we can actually refer it as a communication with external services, yeah, like delivery services, because we are referring to the like out of the scope of the JVM application. We are actually like accessing the C++ libraries like through the GNI. This is actually the out of scope of our talk, and we mark those methods with a native keyword, yeah, in Java. So yeah, as you see, in the stack area we store the local variables, primitive variables, yeah, but it does not guarantee us from the thread safety, because like improper thread safety, we still end up having some race condition or like data race situation, as Farrukhjon before me mentioned about. So yeah, the heap area and the method area. In the method area we actually store the class level data. Yeah, so like meta information, something like that. Yeah, static variables, and yeah, something like that. Okay, so moving on to the execution engine. Yeah, this is another one of the important parts of our JVM application, where the code is being executed. Yeah, because if we create something, we need to execute. Yeah, we need to do some work to prepare something. So we have the objects, we have the ingredients, we have everything. We need whom? We need the person. Like we need the operation. Yeah, to do the job, to do the dirty job. You can see. So the execution engine we can refer to as a cooking team. Yeah, chefs, like chef assistants. Yeah, all the people who are involved in the meal cooking process. Yeah, because without them we cannot actually make any food. So yeah, the main parts of our execution engine is the interpreter and the GIT compiler. Yeah, as I mentioned before, interpreter is also does the compilation of our code, executes the code, but code, or sometimes we might refer to it as instructions, because in fact this is a bytecode instructions. Yeah, so the interpreter reads the instruction line by line and do the job. Yeah, this is in fact the slower one. Yeah, so that's why we can actually say, for example, interns who actually, or like newly started chefs, can be considered as interpreters, because they actually slow. Always they need to be like give all the instructions, because without them they can actually do some jobs like on their own. Yeah, and on the other hand, GIT compilers, like just-in-time compilers, yeah, they actually executed something, and then if it executed twice, they actually store it in a cache, yeah, in order to have the faster compilation. So in fact, that actually differs, like prior, like by what kind of JVM implementations are we using. So the JVM, in fact, can be considered as a specification, yeah, or like abstraction, because we have the different implementations of the JVM. Can somebody have experience working with the different kind of versions of the JVM? Or maybe somebody can actually tell some different versions of the JVM or implementations of the JVM? Yeah, mostly all of you guys use that one, but yeah, but rarely refer to its like official name. In fact, mostly we use the hotspot JVM, yeah, the hotspot implementation of the Oracle JDK. So we have the Oracle Open JDK. So the hotspot implementation is mainly used by the Oracle company, yeah. And different JVM, we have also SAP, yeah, like for the SAP company. And also for the Microsoft, we have the Azure, yeah. Yeah, that's right. And then also we have the Graal VM, yeah. So the Graal VM, also a different version of the JVM, yeah. This is also a like revolutionized how the JVM is being executed, yeah. But in fact, the compiler is not that mature as the hotspots VM's compiler. In fact, the hotspot has like two compilers, yeah, C1 and C2, like the client and server, yeah, because it does the job of the compilation. But in the Graal VM, we have a Graal JIT compiler, which is actually written in Java, but the current compilers in Hotspot VM are written in C++. So yeah, this is the process of the GIT. You can read that. Intermediate code generator, code optimizer, like profiler helps the GIT compiler to know which of the portion of the code has been executed more than once in order to optimize it. And then the code will be generated into the bytecode, yeah, like bytecode instructions. And then, yeah, Java native interface to access the native memory area outside of the GVM, yeah, as you might, like this is a scope of the, like outside of the GVM. We can refer to it as a, like, external services to our kitchen, yeah. And then the garbage collectors. Currently, we have a couple of versions of the garbage collection. So right now, the garbage collection, like in our kitchen example, we can refer to them as a cleaning stuff, yeah? Because we need to clean up our space to prepare more meal. We need to actually like free some space for the other products to be made. Because if there will be remaining, in fact, the garbage collector clean up the shared area, yeah, mainly the heap. And in fact, the heap itself has been divided into the several sections. So here we see, this is the heap, architecture of the heap, yeah, as we described before. So like in our kitchen layout, this is a fridge, pot, yeah, cooking zone, and etc. So the heap itself has been divided into the two parts, young generation and old generation, yeah? Like, for example, old generation is like less cleaned space, yeah? We can consider it as a storage of our food, yeah? Like a warehouse. And the young generation space is like the commonly used space, yeah? Commonly cleaned up space. And inside of a young generation, we have also further two parts, Eden and survivor space. And the survivor space has been split into the two parts, like survivor 0 and survivor 1. So by default, 1/3 of our heap space is a young generation, and 2/3 of it is an old generation. And also, the survivor space are 1/8 of the whole heap area. And also, we have the meta space. This is like after the Java 8, the meta space has been introduced. Prior to the Java 8, instead of the meta space, we used to have a permgen area, yeah? So it was like the heap was a bit big. So right now, meta space is out of the heap area. This is considered as where we, for example, create the new threads in our application. So the threads will live in a meta space because they actually like uses some internal like CI, C++ level codes. So this is a outside of our heap. So yeah, and the garbage collectors, we can say, for example, they work in shifts. Yeah, for example, one half of them like worked in the morning, and then other half. But it depends on what kind of garbage collector do we use. We have the generational garbage collector ones. We have the one-thread garbage collector, which is actually does the stop the world pauses. Yeah, like we don't use the one like stop the world. Actually, stops all the process in our GVM and does all the cleaning up. So this is like a cleaning crew come into the kitchen and like stopped all the cooking process and told the kitchen staff to go away, and then they're actually doing the cleaning up. So this is not how the business should operate, because it will actually lead to the slow performance of our kitchen. So that's why we have the like generational garbage collection. So that's why we have the generational heap, because like young generation, old generation. And then like the garbage collector also cleans up by the generations, yeah? So it first has a one pause, like one process of marking the unused objects in our Eden space, and then cleans up, sweeps all the process. In fact, the garbage collector uses the algorithm called a mark and sweep, and also like mark, sweep, and compact, because generational ones are garbage collectors will lead to the defragmentation of our heap, yeah, because the generational are like not actually stored in one place. So when we have one cycle of the garbage collector, we might have a fragmented areas of our heap, because like some of the used objects will be stored here, some of them will be there, so they'll not be consequent to each other. And then defragmentation, like compaction algorithm, will actually merge them into the one and then delegate to the further survivor area, yeah? And like if they still exist in a survivor, then they will be delegated up to the tenured old generation part, yeah? So we have the properties which we can define the boundaries of our GVM, yeah, like XMS, XMX, like the minimum heap space, maximum heap space, and also we can set up the metaspace area, because if we don't set up the boundary for the metaspace, it will actually take all the memory of our operational system, because it takes the like memory from our operation system, which is underlying of our GVM application, yeah. So yeah, let me also refer, yeah, like as I mentioned before, the permgen, we used to have some problems when we were using the permgen. For example, interning of the strings, when we actually create the string and then interning it like creating it in our heap, we were actually prior to the Java 8, it used to be created inside of a permgen, but it was like leading to the out-of-memory errors, because the permgen is like have the limited space, right? So the out-of-memory errors like really bad. It means like we have to restart our application, and all the process in our application will be lost after the restart. So it will be completely unresponsive. So that's why metaspace has been introduced, and the metaspace has an elastic size. But in fact, if we have really bad application, if we have, for example, deadlocks in our application, yeah, when the one thread is blocking each other, cannot access the same resources, yeah. So like it's like one chef trying to cook some meal, but holding some ingredients, for example, rice, but other chef also wants to cook some meal, like for example, let's call it mastava, but he's holding the meat, but they want to access the rice, and that's why they actually holding a lock, but trying to access which is being locked by another thread. That's in that situation we have the deadlock situation, yeah. In that case, we cannot do anything, because we actually end up having resource starvation. We used all the available component, and then boom, we run out of the space. Like we will get a metaspace out of memory error. So in fact, our GVM tells us where is the problem. In fact, it points out what kind of component we should look at it. So that's actually mainly it. And also, yeah, for the monitoring tools, we can use, as I mentioned before, GVisual VM, JConsole, or like a Java profilers, yeah, to investigate the memory leaks. Because if badly written code lead to the memory leaks, like, you know, like unused objects, hidden objects, for example, if you have like nested classes, yeah, one class has not been used, but it has still the pointer to the another class inside of it. We might have, like if we use the older versions of Java, we might have the situation of the resource leaks, yeah. Or if we like open up the connection, like let's say the producer to Kafka, yeah, or like any other external service, we open up the session, but we never close it. We have the resource starvation as well. We have the resource leak, yeah, because it will actually accumulate those connections and never will be closed. When it will not be closed, it will not be reclaimed back to the heap. So that's why we run out of the space, and boom, we will have the out of memory errors. So yeah, like we need to follow the best practices in order not to have the out of memory errors. But if our scale is too low, we can actually increase our size if the problem is a scale. But that should be the last consideration, because in the first place, we need to investigate our application for any memory leaks. So any questions, guys? Okay, go ahead.
My question will be related to the topic of the Graal VM, which you mentioned during the presentation. I have a question. Did you try to use the native images, I mean the ahead of time compilation in your, the day-to-day work? And if yes, what is your, the opinion about it?
Yeah, in fact, in our production experience, we did use the Graal VM, but for the sidecar. Yeah, the sidecar is a paradigm, like a microservice architectural pattern, which is like deployed alongside of our main application. Sidecar contains all the non-business related logic, yeah, like a logging and everything like related to the authorization and like caching the code, like out of the business scope, yeah. So we actually deployed that in a ahead of time compilation, yeah. We used the Graal VM because it was like because it has to be like small in time, like it has to be like more friendly in terms of the serverless application, yeah. Because in fact, Graal VM is like mostly can be suitable for the like serverless application, like when you have like thread come in, you need to stop, you need to like start up the application in a fast time, like have a faster bootstrapping time of your application, and then when it won't be needed, you need to actually decrease it down. So in that kind of cases, it is more suitable. But again, like the GIT is like not so mature as the hotspots VMs, because in a hotspot we have the kind of two types of the compilations, but still Graal VM is like more like better, I would say, but it has the pros and cons as well, but it's more like for the microservice architecture related, but also it depends, yeah.
Sure. And the second question will be, what is your default garbage collector for, the nowadays services which you write in your work? Is it the newest one like ZGC, or is it the standard one in the GDK? If I'm not mistaken, it's G1 nowadays.
Yeah, G1.
So,
yeah, in fact, that's really nice question. Yeah, that's really good question. But in fact, right now, like in our application, we actually refer to the G1 GC, but it depends on what kind of application we are trying to build. For example, if it's like IoT edge devices, we use the like no GC, something like that. So which is like a kind of different version of the garbage collector, and like but ZGC is like was introduced in like Java 15, and it was like available, but for the Java 17, I guess like G1 GC was the main garbage collector default implementation. But G1 GC is like really mature, like since the Java 11 it has been. And if I'm not mistaken, right now in Java 21, the ZGC has been like default one, or yeah. Because ZGC used to be non-generational one, and G1 GC was like a generational one. And ZGC was using the colored pointers, yeah, like pointing out the objects, but it has a like lower latency. So like ZGC is like mostly can be used for the low latency applications, and like G1 GC, like all other traditional applications can be used. And also we have the Shenandoah, which is also, yeah. In Java 17, it was like also on the testing, and then, if I'm not mistaken, it was reintroduced in Java 21 as well. So yeah, that can be also another big topic to discuss, because yeah, garbage collector itself is like whole new world of our GVM. So yeah.
Sure. Thank you. I have any questions.
Okay, guys, if no questions, yeah. Any more questions? Yeah, please go ahead.
Can we compile our code on Java 11 and then run it on 8? And what about vice versa? Like compile it on Java 8 and then run it on 11?
Well, in fact, Java promised us to be a backward compatible. Yeah, for example, if we actually compile the code in Java 8, we should be able to run it in a Java 11 as well, and further versions of the Java. But it depends. For example, if we have used some of the libraries which was not available, for example, in Java 8, but in a backwards, for example, if we compiled the code in Java 17 and we wanted to run it in Java 8, there might be a problem because there were some new classes were introduced in Java 17, so that's why we might have the issues. Especially, for example, if you use building tools like Gradle and Maven, we might have some issues. It was compiled in 65.0 version. That's actually refers to the Java version, in fact. Because in fact, it uses the underlying Java under the hood to build the application.
Yeah. Thank you.
Thank you for the question. Any questions, guys? Yeah, please go ahead.
I have a question about the metaspace, which was firstly in the garbage collections, and it has now own space, and it's mostly used for non-Java codes to work with them. If I saying wrong, you can mention it.
Yeah, in fact, the metaspace was introduced, if I'm not mistaken, in Java 8. Prior to the metaspace, we have the permgen.
Yes.
It was part of the heap, but metaspace is outside of the heap. It is a native memory space. So mainly, thread allocation happens inside of a native area because we have in C language we have the malloc, memory allocation function. So this actually calls that kind of allocation the thread, because thread is actually traditional threads in Java are referring to the underlying OS thread. So that's why the thread allocation happens to be outside of the metaspace, inside of the metaspace, which is outside of the GVM. So yeah, all other stuff related to the GVM, but mostly in your application you don't need to use the native space at all, because this is for the GDK developers, the people who actually build the tools that we can use for them. So this is actually the next level. If you hopefully will be working at the Oracle, in other companies providers of the GDK, you will be working with the native area a lot, because you need to make it more faster. You need to actually think about it, how to build the kitchen for the people, because you'll not be the person who is actually building the restaurant, making the food, but you will be the person who actually creates the restaurant at all because that's actually the next level it will be. Yeah.
Okay, thank you.
You're welcome.
I'm just curious, what is the need of customizing a new class loader for ourselves?
Yeah, nice question. Well, in fact, for example, we might have some custom libraries, right? And custom dependencies, that we have created, and we can use we can actually use some application class loaders, custom class loaders, because if we wanted to do some optimizations. But in my own experience, yeah, I have not used that one, but in fact that's the possibilities, in fact, yeah, that you can do some optimization, customizations, because for example you might actually change how the application will be loaded. For example, mainly if all the thing is located inside of your class path, all the dependencies will be loaded by the application class loader, which is up to the custom class loader. But if you want to do something outside of your application, outside of your class path, so you can use that custom class loaders to load some necessary information. So yeah.
Thank you.
Welcome.
Yeah.
So if no questions, yeah, thanks a lot, guys. Yeah, that's it from my side. Thank you.
Thank you, everyone. And now we're going to our last part, which is where we can tell you about family hobbies and then some career opportunities.
Hello, My name is Dmitry Pamutkin. I'm a software engineer team leading in EPAM, co-head of Java practice in EPAM Uzbekistan, delivery manager, and Java Kotlin software engineer. I want to speak about EPAM. This event was created with EPAM Java Uzbekistan community with support of MGC School. And we want to say a couple words of us in conclusion of the event. First of all, EPAM it's more than 60,000 engineers that create the software all over the world. How we see the most our clients, it's Americas and Europe and Middle East. That means we can offer experience with development software engineer with top companies. Here you can see geography of EPAM. One dot, it's around 500 employees, and you can see we all over the world. But let's speak about EPAM Uzbekistan. EPAM Uzbekistan is more than 600 employees. And actually, when this client created, after that, I already hired employee on Nukus, and I can to say we all over Uzbekistan. But let's talk about seniority. How we see our seniority is very strange, and we try to hire more engineers that only start their career. Because we're interested in one, A2, yes, we're interested in more experienced engineers, but for create engineers who want to start career, invest in local IT education. Let's speak about education opportunities, what EPAM offer. First of all, it's MGC school. It's absolutely free. You can join in any moment. It's community-based. Main focus of this opportunity is for who don't have experience at all at Java, who want to start their career. You can offer this to your friends, and maybe they can join. But it's not main topic of this education. It's not hiring for EPAM. That means we have second opportunities, EPAM campus. This is for who already have some experience, not only Java. How you see, we ready to educate for many specialties. But if we're talking about Java, if you have basic experience, you have not production experience, you can just try to join, and after continue, you pass EPAM training center, we can offer you job. And one more, what EPAM invests in Uzbekistan, EPAM and IT Park created IT Park University for people who want to be graduated in IT. In this year, first group was graduated and already launched a master's degree, opportunity to receive master's degree in Uzbekistan. And we also see on who ends the university, and the best of who ends, we do an offer. This is about learning opportunities. That's all, but I want to add, if you're interested in EPAM, you also can go to epam.com, fill the form, add your resume, and we connect with you. Thank you. Any questions, maybe?
That's gonna be the end. Thank you everyone for coming. See you on our next events. Yeah, I'm finally so.
Yeah.